Hey everyone, and welcome back to the channel. Have you ever looked up at the night sky and wondered how hot those twinkling stars really are? It's not like we can send a giant thermometer to the sun, right? So how do scientists measure the temperature of something trillions of miles away? The answer is more incredible than you might think, and it all starts with a much bigger question. What is temperature anyway? For most of human history, temperature was just a feeling, hot or cold. It wasn't until the 17th century that scientists like Galileo Galilei started to quantify it, creating early devices called thermoscopes. But the first true thermometer with a reliable scale was invented by Daniel Gabriel Fahrenheit in the early 1700s, using a simple but brilliant idea: thermal expansion. As a liquid like mercury gets hotter, it expands and rises up a narrow tube, giving us a measurable number. Now, what about the other end of the spectrum? How do we measure temperatures so cold that even our breath would freeze solid? We're talking about temperatures near absolute zero, 0 Kelvin, or minus 273 Celsius, the point where all atomic motion stops. This concept was first introduced by Lord Kelvin, who realized there had to be a lowest possible temperature. But reaching or even measuring something so extreme is far from simple. At these frigid temperatures, liquid thermometers are useless. They would either freeze solid or stop responding. So instead, scientists rely on the electrical properties of materials. One method uses a resistance thermometer, or RTD, often made of platinum. Here's the trick. As the temperature drops, atoms vibrate less, and the resistance to electric current decreases. By sending a tiny current through the platinum and measuring resistance, we can calculate the exact temperature. Modern digital thermometers often use a thermistor, a semiconductor whose resistance changes dramatically with temperature. These are extremely sensitive, making them perfect for cryogenic experiments with liquid nitrogen or liquid helium. For even broader ranges, there's the thermocouple, two different metals joined at one end. When heated or cooled, the junction produces a voltage proportional to the temperature. That's why thermocouples are used everywhere, from spacecraft to jet engines. They're rugged, reliable, and don't need delicate liquids. At room temperature, around 20 to 25 degrees C, and human body temperature, about 37 degrees, traditional thermometers work perfectly. This is where Fahrenheit's mercury thermometer and later alcohol thermometers became everyday tools. Mercury is great for higher ranges, but alcohol doesn't freeze as easily, making it handy for colder climates. Think about it. When a doctor checks your fever, they're relying on the expansion of liquid inside that slim glass tube. In kitchens and factories, more rugged instruments come in. Bimetallic strip thermometers, for example, are used in ovens and thermostats. They're made of two metals bonded together that expand at different weights when heated. As they bend, a dial moves to show the temperature. No mercury, no electronics, just clever physics. And in our digital age, everyday gadgets like air conditioners, fridges, and digital thermometers use thermistors. Now, let's swing to the other extreme. How do you measure the temperature of a steel furnace, or even the surface of the sun? A glass thermometer would vaporize instantly. For incredibly high temperatures on Earth, like in a blast furnace, scientists use pyrometers. A pyrometer is basically a thermometer that never touches what it's measuring. Instead, it detects the thermal radiation objects give off. Everything above absolute zero emits radiation, and the hotter it is, the more intense and shorter the wavelength of that radiation. That's why molten metal glows bright orange. The color itself is a temperature clue. Pyrometers read that glow and calculate the temperature safely from a distance. This same idea works on a cosmic scale. We can't dip a probe into the sun, but we don't have to. The light from a star is a natural thermometer. Enter spectroscopy. Imagine holding up a prism to sunlight. You see a rainbow, but zoom in closer and you'd find dark lines cutting through it, called absorption lines. Each chemical element leaves its own barcode in this rainbow. By studying these spectral lines, scientists can figure out what a star is made of and how hot it is. The physics behind this is called Wien's displacement law. It tells us that the hotter something gets, the shorter the wavelength of light it emits. Think of it this way. A candle flame glows orange at about 1000 Celsius. The surface of the sun shines yellow-white at about 5500 Celsius. The hottest stars blaze blue at 20,000 degrees or more. So just by analyzing a star's color, astronomers can estimate its surface temperature with surprising precision. In fact, this is how stars are grouped into categories like O, B, A, F, G, K, and M, the famous stellar classification system. Our Sun, for example, is a G-type star, yellow, stable, and not too hot or too cold by stellar standards. From the frozen depths of a cryogenic lab to the fiery core of a distant sun, our ability to measure temperature without a thermometer has opened up an entire universe of knowledge. It's a testament to human ingenuity and the power of observation. The next time you look at the stars, remember that their colors aren't just beautiful, they're a direct measure of their fiery temperatures. Thanks for watching. If you like this video, be sure to hit that like button and subscribe for more mind-blowing science content. See you next time!